Good afternoon, everyone. Today, the Atom Seminar has the great pleasure of welcoming Professor Doros Theodorou. Professor Theodorou received his bachelor's degree from the National Technical University of Athens and his master's and PhD degrees from the Massachusetts Institute of Technology, MIT. After that, he was a full professor at UC Berkeley for 9 years, and then he returned to Greece, become a professor at the National Technical University of Athens. His research focuses on the development and application of new hierarchical computational methods for understanding and predicting properties of materials from chemical constitution. So once again, welcome, Professor Theodorou. Thank you so much for being here, and please feel free to start the presentation.
Thank you very much for this very nice introduction. It's really a pleasure and an honor to be giving this seminar, and I congratulate you for this excellent initiative. This series of seminars is really very informative, for me at least. So I'll try to share my screen. Hopefully you are seeing the presentation now.
Yes.
Is it okay?
Yes, you can go ahead.
Okay, so our subject this afternoon will be polymers. We'll see how we can try to predict their properties from atomistic and mesoscopic simulations. We will first remind ourselves of the multiple length and time scales which govern polymer properties. And then we will speak about polymer melts from the point of view of predicting packing, entanglements, and rheological properties. Next, we will go into polymer glasses, where we will be concerned with predicting elastic constants and the very gradual process of structural relaxation in the glassy state. And then we will say a few things about polymers at interfaces, namely how can we predict surface tension, work of adhesion, and even the mechanical behavior, interfacial shear strength between a polymer and a nanofiller in a nanocomposite material. So it is, of course, extremely nice to be able to predict properties from chemical constitution based on statistical mechanics and molecular simulation. In dealing with polymers, one is faced with a serious challenge, and this is that the length and time scales that govern the properties of polymers spread over very, very broad spectra. So we have many, many length and time scales. And in terms of length scale, if you think of an amorphous polymer, we have structure at the level of bond lengths and atomic radii on the level of angstrom. We have structure at the level of the statistical or Kuhn segment length, which is defined such that the whole chain can be envisioned as a random walk consisting of these Kuhn segments. For typical flexible polymers, the length of a Kuhn segment is on the order of 1 nanometer. We have structure at the level of an entire chain that is quantified by the chain radius of gyration. And for usual molecular weights, this can be 10 nanometers or longer. And we may have phase or microphase separation phenomena in the polymer, leading to domains which may be 1 micrometer or even larger in size. Even broader is the spectrum of characteristic times that we have in polymers. If we consider bond vibrations, their periods are on the order of tens of femtoseconds, very, very fast. If we consider conformational transitions, gauche trans isomerization, for example, in a polyethylene melt, the waiting times for those are on the order of 10 to the minus 11 seconds. If we consider longer and longer sequences of chains, the time they require in order to rearrange and change, forget their conformation, is longer and longer until we reach the longest relaxation time of a chain, the time that is required for a chain to diffuse by a length commensurate with its size and forget its conformation. And for even modest molecular weights, this can be milliseconds or longer. If we have phase and microphase separation phenomena, these may have characteristic times of seconds. And if we go to the configurationally arrested glassy state, where the system is not in equilibrium, it is very gradually trying to reach equilibrium, the processes of physical aging 20 degrees below TG can have times on the order of years or longer. So from bond vibrations to physical aging in the glass, we have 21 degree orders of magnitude on the time scale. And clearly, all this cannot be addressed by a single simulation approach. By comparison, if we consider atomistic molecular dynamics, which is the most common simulation method to predict properties, this can go up to microseconds on ordinary Beowulf clusters, for example. It can go to milliseconds on special hardware, but it can certainly not address these very long times that we encounter in polymers. What do? We try to develop hierarchical modeling and simulation methods, which consist of many interconnected levels: electronic, atomistic, mesoscopic, and continuum, each level informing the more coarse-grained ones, so that in the end we may be able to connect the chemical constitution to the macroscopic properties. Here we will focus primarily on atomistic and mesoscopic simulations, the boundary between the two being set rather arbitrarily at 10 nanometers and 100 nanoseconds. So let's first look at polymer melts. We're interested in polymer melts because polymers are processed in the melt state, and typically we have very long molar masses in these melts. How can we equilibrate them? We said molecular dynamics cannot reach the times that are relevant in these melts. Since a very long time in our group, we have been developing Monte Carlo methods to fully equilibrate polymer melts of very long chains. And these employ moves which change the connectivity among the polymer chains. An example is the so-called double bridging Monte Carlo move. Envision two chains near each other in the melt. We have a move which excises a trimer segment from the blue chain and a trimer segment from the red chain, and then builds two new trimer bridges to form two new chains, which have exactly the same length as the original ones, but very different conformation. So by using this kind of move, we are able to very boldly rearrange the long-range conformational properties of polymer melts. We are able to have very efficient sampling of these long-range conformational properties, and we can equilibrate a polymer melt orders of magnitude faster than molecular dynamics. Here is an example of equilibration of a long-chain polymer melt. We're speaking of polyethylene melts, which are represented by boxes filled with chains with three-dimensional periodic boundary conditions. Here is one such chain, 6,000 carbons long. We use the Trapi force field, an ordinary force field for alkanes that was developed by Ilya Siepman and collaborators. And if we equilibrate a linear polyethylene, we're able to get volumetric properties. For example, at 450 Kelvin and 1 bar, this is how the specific volume varies with chain length across a homologous series of polyethylenes. We see a hyperbolic dependence of the specific volume on the chain length, which is very close to experiment. And also we can accumulate pair distribution functions from the equilibrated simulations, and by Fourier transformation we can get static structure factors, the X-ray diffraction pattern. So here you see the X-ray diffraction pattern as a function of the wave vector for polyethylene again in the melt state. There is a first peak which is intermolecular in origin. It reflects intermolecular correlations between the carbons in the system. It's the amorphous halo. And then there are other peaks which reflect the intramolecular bonded geometry of the chains. Both are predicted very well in comparison to simulation, to experiment. So we can equilibrate long-chain polymer melts. The fact that we can equilibrate long-chain polymer melts means that we can also try to analyze entanglements between chains in these melts, because entanglements are very important in determining the rheological properties and the mechanical properties of large deformations. For this purpose, we and other groups have developed algorithms. Our algorithm we call CRETA, contour reduction topological analysis. It starts with a well-equilibrated configuration of the melt. It fixes the chain ends. For example, these white balls that you see here are chain ends of polyethylene chains. And then it proceeds to reduce the contours of all the chains present under the condition that no two chains can cross each other. And as the reduction proceeds, the diameters of these chains are also reduced. So in the end, the atomistic configuration becomes a set of zigzag lines coming together at topological constraints with a coordination number of 4. And these topological constraints are our picture of entanglements, and the zigzag lines that go through them are our picture of the so-called primitive paths that were envisioned by Sam Edwards in connection with entangled polymers. So one can then go into this network of entanglements and analyze quantitatively. And here are some results for such an analysis for a variety of polymer melts, polyethylenes of 2 different molar masses, polybutadiene, polyethylene terephthalate, atactic polystyrene. And we have shown here the Kuhn length of a primitive path, or the entanglement tube diameter, as it is called, this D, which is nothing else than the mean squared end-to-end distance of the chains divided by the mean length of the primitive path, and also the molecular weight between entanglements, ME, which is again obtained from the molecular weight of the chain and these properties. And as you can see, the results that are obtained from the topological analysis compare quite well from estimates based on rheological properties. Also shown in the last column here is the so-called packing length, which is obtained from the molar mass, the density, and the mean squared radius of gyration of the chains. And it is essentially a measure of how fat the chains are in relation to how stiff they are. You can see, for example, it is much bigger for polystyrene, which has these phenyl rings sticking out of the chains. And what we see is that the simulation estimates obey an empirical relation that has been proposed for estimating molecular weight between entanglements based on the density and the packing length. And that is obvious because both the packing length and the entanglement properties are predicted in very good agreement with experiment. Now, can we say something about the rheology of these melts, which is of interest in polymer processing? We just mentioned that we cannot address the dynamics of very long chain entangled polymer melts because of the very long relaxation times that characterize these melts. But perhaps we can develop a coarse-grained approach for this dynamics. So that's what we set out to do. We employ a coarse-grained representation for the polymer, where each chain is represented now as a sequence of beads and springs. And each bead stands for something like 50 skeletal atoms. It is quite an aggressive coarse graining that we're introducing here. The beads are connected to each other through springs, which represent the entropic elasticity of these strands that are represented by the springs. And in addition, to represent entanglements, we introduce what is called slip springs. This you will find in a number of relatively recent articles in the literature. A slip spring is a spring that connects 2 internal nodal points on 2 different polymer chains. And it is thought that each end of a slip spring can execute hops between adjacent beads along the chain, so the slip spring can slip along both the chains that it connects, and in this way it introduces an entanglement. Of course, we envision that this slippage process, this hopping process, is characterized by a rate constant. So we have to introduce a rate constant to describe the dynamics of these hops executed by the ends of the slip springs. When a slip spring reaches a chain end, it may choose to jump out of the chain, in which case we'll lose the entanglement. However, continuously, chain ends try to entangle with other chains in their surroundings. And again, this is also viewed as an activated process characterized by a rate constant. So at equilibrium, you have a concentration and equilibrium concentration of entanglements or slip springs as a result of these destruction and creation processes of the slip springs. So this coarse-grained or mesoscopic simulation from a technical point of view is a Brownian dynamics coupled with kinetic Monte Carlo. Brownian dynamics is so that we can move the beads in three-dimensional space. And kinetic Monte Carlo describes these infrequent events, these hops, and the creation of slips, of slip springs at chain ends. Of course, we need an effective energy function, a free energy essentially, with respect to the bead positions and the connectivity of the polymer. And that consists of both intra and intermolecular contributions. For the intra-chain effective potentials, we simply Boltzmann invert the distributions of end-to-end distances of strands as they're obtained from atomistic simulations of a relatively small molecular weight melts. So we get something like a nonlinear spring of finite extensibility that describes the intramolecular interactions between the beads. And as regards the non-bonded interactions, we use a free energy density, which is dependent on the local density and derived from the equation of state. In our case, we use the Sanchez-Lacombe equation of state, which describes quite well the volumetric properties of the atomistic simulations and also of experiments. So in this sense, we have a hybrid particle field approach because the intramolecular contributions are represented in a particle sense as interactions between particles. The non-bonded contributions are represented in terms of a density field. And of course, this density is shaped by where the beads are. In addition, we need a friction coefficient to describe the dynamics in the Brownian dynamics, and that we extract from atomistic molecular dynamic simulations, from molecular dynamic simulations of oligomers. And also we need slip spring hopping rates. These are related to the bead friction factors. So we can parameterize this mesoscopic model essentially with no adjustable parameters based on the atomistic simulations of small molecular weight analogs. Now, if we use this model, we can try to get out some properties, and you see here some rheological properties. On the left-hand side, you see the zero shear viscosity of polyethylene again melts over a variety of molar masses. You see that there are some atomistic simulations from molecular dynamics here. These are shown with the blue triangles, and they are necessarily confined to low molecular weights because we cannot address the long times of the longer chain systems. However, with the mesoscopic approach, we can go to larger molar masses. So you see two sets of results, the green points, which come from equilibrium Brownian dynamics kinetic Monte Carlo, and the red squares, which come from non-equilibrium Brownian dynamics kinetic Monte Carlo under conditions of steady shear flow. And the two sets are exactly the same, which sort of points out to an internal consistency of this approach. And we see that we can indeed predict viscosities for these long chain melts, and the dependence on the molecular weight is pretty much what is seen also experimentally with these black points and the yellow star here, namely that the zero shear viscosity for long chain melts goes like molecular weight to the 3.4 power. This is a signature of entangled dynamics. On the right-hand side, we see the viscosity as a function of the shear rate imposed on a melt under conditions of steady shear flow. Essentially, we have used Lees-Edwards boundary conditions with exactly the same mesoscopic simulation that we described, and we are able to look at viscosity essentially as the ratio of the shear divided by the shear rate, gamma dot. And instead of the shear rate, we use a dimensionless quantity here, the Weissenberg number, which is the shear rate multiplied by the longest relaxation time of the melt. What we observe is that at the low Weissenberg numbers, when, in other words, the flow is slow, it is gentle, the shear viscosity assumes a plateau value. This is the so-called Newtonian plateau. And it's exactly this plateau value that we were plotting in the left-hand side plot. However, when we have fast flows, when the Weissenberg number is very large, we see that the viscosity goes down with shear rate. We have, in other words, shear thinning. And this can be described by a power law, the power being minus 0.7 between the Weissenberg number and the viscosity. This is quite close to what experimentalists measure in these molten polymers. The mesoscopic simulation, of course, can give you what happens at the molecular level and what is responsible for this nonlinear viscoelastic behavior of the melts. So what we show here is the end-to-end distance distribution, the distribution of end-to-end distances of chains for two melts of polyethylene of roughly 7,300 and 30,000 grams per mole molecular weight for a variety of Weissenberg numbers. And one can see that when the Weissenberg number, which again is this dimensionless shear rate, is low, below 1, for example, the chains assume conformations which are typical of equilibrium, essentially Gaussian conformations. However, when the flow is very strong, when the Weissenberg number is very large, then the chains are unraveled by the flow, and this end-to-end distance distribution becomes very broad. You have some very extended chains in the system. And in addition, the chains strongly orient. What we show on the right-hand side is essentially second Legendre polynomials, which reflect the orientational tendencies of the end-to-end vectors of the chains. They are functions of these angles theta between the end-to-end vector and a coordinate axis. And we see that whereas at low Weissenberg numbers, this order parameter P2 is 0, there is no orientational preference for the chains. For strong flows, there is a definite tendency for the chains to orient parallel to the x-axis, the axis of the velocity, and normal to the y and z axis. Actually, there is also a small difference, as you see, between the y and the z directions, and this gives rise to what is called the second normal stress difference in these flowing melts, which is calculated along with the first normal stress difference in quite good agreement with experiment. So this mesoscopic model can give us a good grasp of these nonlinear viscoelastic properties for longer chain lengths that could be simulated with atomistic simulations. We have a gain of roughly 3 orders of magnitude in relation to atomistic molecular dynamics when we invoke these mesoscopic simulations. Another thing that is very much of interest for polymers is the so-called dynamic mechanical moduli. This refers to the response of a polymer to an oscillatory torsion experiment, which imposes an oscillatory shear on the sample. So you impose an oscillatory shear deformation and you measure the stress. And there are 2 contributions to the stress. One part which is in phase with the deformation that we impose, and this is described by the storage modulus G prime. And there is another part which is 90 degrees out of phase with the imposed modulus, the imposed deformation, and that is the loss modulus G double prime. G prime measures the elasticity, G double prime measures the dissipation as you deform this viscoelastic material. And both these moduli are functions of the frequency or angular frequency of the periodic deformation imposed. So we can get these properties from the mesoscopic simulation. First of all, we get the stress relaxation modulus from the time autocorrelation function of the shear stress. And then we Fourier transform it, and we get G prime and G double prime. And here they are from the mesoscopic simulations with the red points. The G prime is the filled red points, the G double prime is the open red points. And it is being compared with experimental measurements for this polymer, which is cis-1,4 polyisoprene, essentially natural rubber, uncross-linked. And we see a pretty good agreement for relatively close molecular weights. Of course, this is a very strong function of the molecular weight. What is particularly gratifying is that we can calculate these moduli at low frequencies. You see that the frequencies here are on the order of 100 inverse second. These are very long time scale phenomena that could not conceivably be captured by a molecular dynamic simulation at the atomistic level. However, the mesoscopic simulation can get them. Now, one is also interested in the so-called segmental dynamics of polymers. This is the local dynamics that is frozen when the system becomes glassy. And as long as you are in the melt state, you can probe the segmental dynamics by atomistic molecular dynamic simulations. For example, here we see some results from simulations of long chain polystyrene. The way we quantify the segmental dynamics is we define specific vectors affixed on the chains. For example, the vectors connecting the phenyl rings to the backbone, and we accumulate time autocorrelation functions of these vectors, which of course decay with time. This P1 of t, for example, decays with time as shown in this semi-logarithmic plot. Now, if one integrates this P1 of t, one has a correlation time, and it is very customary to plot the logarithm of this correlation time as a function of inverse temperature. As you can see, this plot is nonlinear. In other words, the dynamics is non-Arrhenius as regards its temperature dependence. If you go to lower and lower temperatures, the correlation times become disproportionately high, and that is associated with hierarchically constrained dynamics as one sees in glass-forming systems. Now, this kind of dependence, this nonlinear dependence, is very frequently described by a Williams-Landel-Ferry or a Vogel-Fulcher-Tammann expression relating the relaxation time with the temperature. So if one fits this line that comes out of the molecular dynamics simulation with this WLF relation, one can extract an estimate of the glass temperature, and here it is, roughly 380, which is not very bad when one compares it to the experimental one, which is 373. Also shown here are measurements from a considerably lower molecular weight polystyrene. The simulated one was 152 kilograms per mole. The measured one, 1.87 kilograms per mole. And these gray points here are measurements from dielectric spectroscopy, which measures exactly this type of motion, and they parallel the measurements that were done in the simulation. One can also look at how the carbon-hydrogen bonds reorient as a result of thermal motion, both the aromatic and the aliphatic ones. And in a similar fashion, this time one can calculate a second Legendre polynomial reflecting the time, the correlation of these bonds, the way in which they forget their original orientation, and accumulate again a correlation time as a function of inverse temperature, which now can be related to NMR measurements, because this is the type of motion that is probed by NMR. And the agreement is again very good. So if one uses a reasonable force field to describe the polymer and does atomistic molecular dynamics in the melt state, one has a good handle on these segmental motions that participate in the glass transition. How about, though, a glass itself? Can we simulate a polymer glass? Now, polymer glasses, and in general glasses, are a tremendous challenge for simulators because they are non-equilibrium materials. Their properties and their structure, they depend on the history of formation of the glass. And in order to simulate a polymer glass since some time now, we have invoked the inherent structure picture that was proposed by Frank Stillinger and many other scientists working on glasses. Namely, we assert that a polymer glass is trapped in the vicinity of a local minimum of its potential energy with respect to its microscopic degrees of freedom. So this X here, which is represented as one dimension, is in reality the coordinates of all atoms that span the configuration space of the polymer. The potential energy is a very rugged function of this configuration, and it has many local minima. And the glass tends to be trapped in the vicinity of a local minimum or inherent structure, executing vibrational motions within a basin that surrounds this local minimum. Now, the basins are in general separated by high potential energy barriers that cannot be overcome at the prevailing temperature. There may be, of course, basins nearby each other which have lower barriers separating them from each other that can be overcome at the prevailing temperature. And such a group of basins that communicate easily with each other is called a metabasin. Largely, however, the dynamics of this material is configurationally arrested. This is a one-dimensional picture. Here is a two-dimensional picture from Chris Delago to give you a better perspective of how this rugged energy landscape would look like. In reality, we're speaking of 3n coordinates here of the full configuration space of the polymer as X. So transitions between different basins or minima are inhibited by high energy barriers. And if we have a real glass, we envision that its properties are arithmetic or quenched averages of the corresponding properties of the individual basins of attraction in which the glass is arrested. Of course, the distribution among these basins is governed by the history of formation of the glass. A restricted equilibrium is established within the basins and metabasins, but full equilibration is inhibited by the large energy barriers. With time, however, the configuration of the glass may have the chance to overcome some of these barriers and tend very slowly to an equilibrated Boltzmann distribution, so to speak, across the energy landscape. So this is exactly what is physical aging. Gradually, the properties of a glassy material change with time, but this is an extremely slow process. So our first concern in simulating a glass is to form specimens of this polymer from an equilibrium melt by rapid cooling from the melt, and we do so with molecular dynamics. So we cool a melt, we quench it, and we trap it within local minima of the potential energy with respect to configuration, to configurational degrees of freedom. As long as this glass is trapped in the vicinity of a minimum, we expand its potential energy with respect to its microscopic degrees of freedom out to second order. It sits at a minimum, so the gradient of the potential energy is 0. But this is a very important term, the second order term. This H is the Hessian matrix of second derivatives of the energy with respect to the atomic coordinates. And by diagonalizing this Hessian, we can obtain normal modes for the vibrational motion of the glass while it is configurationally arrested in the vicinity of this minimum. Each such normal mode of vibration is associated with a vibrational partition function. So we can define a vibrational free energy, which is added to the energy of the minimum, or the inherent structure energy, and gives us a Helmholtz energy for the glass as long as it is trapped in the basin. It is important to realize that the inherent structure energy and the eigenfrequencies are functions of the spatial extent of the system. If we change the dimensions of the system, both the inherent structure energy and the omegas, the frequencies, change. So essentially, this here is a fundamental equation of thermodynamics for the arrested material that gives us the free energy as a function of temperature and the spatial extent. And we can use it as a starting point for getting thermodynamic properties for the glass. Using this quasi-harmonic approximation within the basins in polystyrene glass, based on 5 basins, not very many as we see here, we can accumulate, for example, the specific volume as a function of temperature. And here I show you these results. The force field is based on a previous work by Alexei Lyulin. Essentially, we impose a pressure of 1 atmosphere on all sides at each temperature on the box, and then we let the box go to the configuration that would correspond to the minimum of the free energy with respect to the dimensions of the box. And that volume, the volume we plot as a function of temperature. You see 2 sets of results. One is quantum mechanically calculated, the quantum mechanical vibrational partition function. The other one is classical. They are very close to each other because the temperatures are rather high here. And they lead smoothly into the melt behavior. The blue points here are melt predictions for the volumetric properties of the polymer. So there is a clear break in the slope of the specific volume versus temperature, which is a characteristic of the glass. The glass temperature is around 100 degrees centigrade, or 373 for real polystyrene. And it so happens that these data points are not very far from that. So we see that this quasi-harmonic approximation gives us a measure of the expansivity of the glass that is not too bad when compared with experiment. Another thing that you can do for these glasses is you can perform mechanical deformation experiments on them. You can, for example, impose a stress tensor such that there is a tensile stress in the x direction, whereas the y and z directions are exposed to 1 atmosphere. Or you can even impose a compressive stress in the x direction. And you can again minimize the free energy and observe at what dimensions the system equilibrates when it is confined in its basin, and then average over many basins, in this particular case 200 basins, to get a stress-strain dependence. If the stress that you impose is relatively low, this stress-strain behavior is linear and reversible. You have, in other words, elastic response out of the material. So from the slope, you can calculate the Young's modulus, and from the lateral changes in dimensions of the specimen, you can calculate the Poisson ratio. And here are shown these as calculated from the quasi-harmonic approximation imposed on the many configurations of glassy polystyrene that we generated. You can also change the temperature and probe how these properties change with temperature. Of course, the higher the temperature, the softer the material will become. And here are shown the temperature derivatives of the Young's modulus and the Poisson ratio, which are certainly not in perfect agreement, but they are quite close to what one sees experimentally. So this idea of using the quasi-harmonic approximation within the basins where the system is trapped gives us a good handle on the elastic properties of a glassy polymer. Now, could we possibly address this phenomenon of physical aging that we mentioned, the fact that a glass gradually changes its properties with time? Now, in order to do that, we need to probe transitions from one basin into another one. And that is quite a bold and ambitious, of course, goal. But what we try to do is we start from a basin, we start from a local minimum, and we try to calculate as many as possible saddle points around this minimum in the multidimensional configuration space of the glass. Having determined one saddle point, we can then undergo a steepest descent construction in energy and go to another minimum on the other side. So we have two minima, A and B, in this example, which are connected across a saddle point. And we can construct the entire reaction path or transition path that leads from minimum A to minimum B. Having now these properties of the reaction path, we can use harmonic transition state theory to calculate rate constants for the transition from A to B and from B to A. And we can repeat that for other transitions leading, for example, from A to C, or transitions leading from B to other minima, D in this example. So gradually, we can let the system explore more and more minima, starting from a given minimum A, and at the same time, calculate the rate constants for transitions between pairs of these minima. This is one elementary transition to give you a feel of what this is about. This is, again, polystyrene, a rather small box of polystyrene, as you see. This is a minimum. The system is in a minimum of its potential energy, and we can have a transition going over a saddle point into an adjacent minimum. And you see that there is a very subtle rearrangement that changes many things in the system and goes from one minimum to the other. And this is the energy profile of this transition. We started at a minimum, we ended up at a different minimum, and we go over a saddle point. And here we represent the Euclidean norm of how much we have moved in configuration space. So the saddle point appears as a maximum. Once one has this energy profile, one can calculate the rate constants, as we know, for example, for chemical reactions. So we start from a minimum, and we gradually discover more and more minima going across saddle points in configuration space. The blue dots in this graph here symbolize what we call explored minima, minima for which we have calculated as many as possible saddle points leading out of them. The black dots are boundary minima, as we call them, or boundary states. They are minima which are connected to explored states, but not yet explored themselves. And one sees that there is a very rich connectivity in multidimensional configuration space. For each pair of minima, we know the rate constants between them, which are symbolized by these double lines. So one can use this picture in order to try to examine how the system would relax with time. One can initially place the system within a given minimum, for example, within this red dot, that is one minimum in configuration space. The probability of occupancy of the minima in the network is described by a set of master equations, such as this one, which essentially say that the probability of occupancy of a minimum changes with time because of efflux from that minimum into other minima, and that's what is represented by the second term here, and because of influx of probability from neighboring minima. So one can attempt to solve this set of master equations within a network of minima, which is continuously expanding in time, so as to accommodate the fact that at long times the system will go farther and farther in its configuration space. And we have developed such a simulation approach which solves the master equation in a gradually expanding set of minima, and observes how the probability distribution among these minima changes with time. Here we see the clock running in this simulation, and you see the colors changing because whereas originally all the probabilities was placed in one minimum, now it is spreading to other minima through these transitions across saddle points. So in the end, one can observe the system for a rather long time. In this case, it was a millisecond at which the simulation stopped. So one has the probabilities of occupancy of these minima, and one knows what the minima are. So one has also the properties of these minima. So one can try to calculate the properties of the relaxing glass. What we show here is the efflux of probability from the current state of explored states into other states as we augment this network of states. We start with one state, then go to 10, to 100, to 200, to 300 states, and so on. And we explore the efflux of probability from the explored set of states as a function of elapsed time. And what is remarkable is that if you incorporate a sufficient number of states or minima, you see that the shape of this curve of the probability efflux as a function of time sort of converges into a certain form, which is characterized by well defined maxima. So you have a peak, for example, at 10 to the minus 10 seconds, and another peak at 10 to the minus 6 seconds. And these reflect certain molecular processes occurring within this glass. Here I show these time constants as obtained from the landscape picture, the 10 to the minus 6 and the 10 to the minus 10 seconds at room temperature in a log relaxation time as a function of inverse temperature plot. And it seems that these characteristic times that are obtained from the landscape simulation are representative of what is called gamma and delta relaxation in polystyrene, as measured experimentally by direct spectroscopy and neutron scattering measurements, which are shown by these red triangles and these petrol-colored rings, respectively. On the same plot, I show you relaxation times that were obtained for the melt above the glass transition temperature through this process of observing the orientational relaxation of characteristic vectors on the chains. And we have this characteristic non-Arrhenius dependence that we mentioned, shown by these purple squares. And that again seems to be representative of what experimentalists measure as the alpha relaxation, which is associated with the glass transition. So this landscape picture allows us to go to lower temperature and observe at least the segmental subglass relaxation processes that are present in a glass. And hopefully, if we run long enough, this may even give us the beta and even the alpha relaxation within the glass system, which is completely impossible to get by molecular dynamics. Now, a few words about interfaces, since they are so important in the nowadays materials world. It is quite straightforward to simulate free surfaces of polymer melts, or polymer melts sandwiched between solid surfaces, solid polymer interfaces, in other words. Here you see pictures of a polyethylene film characterized by two-dimensional periodic boundary conditions and exposed to vacuum on both sides, and the same film being capped by graphite phases at the top and the bottom. Of course, we need a potential to describe these interactions, and we used Steele's potential in this particular case for the graphite. Now, from a well-equilibrated simulation, Monte Carlo or molecular dynamics, you can actually calculate the normal and tangential transverse stresses in the interfacial regions, and via the Irwin-Kirkwood or the Harashima expression, you can calculate the surface tension for the melt or the interfacial tension. And here, for example, are the surface tensions of this free film as a function of molecular weight at 450 Kelvin, based on the Trappi force field and the Steele potential for, well, rather, there is no graphite here, it's just the polymer. And you can see that the surface tension rises with increasing molecular weight. The simulation points are the red and the blue, and that is as also seen experimentally. When you increase the molar mass of a polymer melt, you increase the surface tension until you reach a pretty much asymptotic limit, which is at this temperature on the order of 26 millinewton per meter for the polyethylene, and it is not too badly predicted by the simulation. If you do similar things to calculate the adhesion tension, you can also calculate thermodynamic properties for the interfaces, work of adhesion, work of immersion, and work of spreading. These are functions of the interfacial tensions for polymer solid, polymer vacuum, and solid vacuum. And here they are shown as functions of the temperature with the corresponding points. The work of adhesion is the red points, for example. And what you see with the broken lines is an approximation to these properties based on the so-called Girifalco and Good expression, which claims that the work of adhesion should be 2 times the square root of the product of the surface free energies of the polymer and the solid. And it works very well in these cases because the interactions are of a London dispersion type. More importantly, one can try to calculate mechanical properties for interfaces. So we tried to quantify the degree of mechanical cooperation that would be present between a polymer, in this case an epoxy resin, a glassy polymer of a rather complicated structure, and a nanofiller, in this case a graphene sheet. So we formed epoxy out of the monomer and the curing agent, the cross-linking agent. This is a very densely cross-linked glassy polymer. Of course, simulating the polymer itself is quite a long story because one has to essentially mimic the reactions whereby these networks are formed, but we managed to do so. And within the polymer, we enclosed a graphene sheet. What you see here is the profile of a graphene sheet. This graphene could be either pristine graphene, pure graphene, or it could be defective. We could pluck out some carbon atoms out of it, or we could plant some OH groups on the graphene to form what is called graphene oxide, because we wanted to look at the mechanical properties as a function of the chemical constitution of this nanofiller. And having equilibrated this interfacial system with 3-dimensional periodic boundary conditions, we essentially performed experiments. We performed experiments which imposed a force on the graphene towards the right, and an equivalent opposite force on the polymer towards the left, and observed how the system would respond to the imposition of this force that shears the interface. When the force is very low, nothing happens. Essentially, the system continues to fluctuate. But when the force is sufficiently high, then there is damage of the interface. You get essentially pull out of the graphene with respect to the polymer. And to define what we call the failure of the interface, we said that whenever the displacement of the graphene in relation to the polymer exceeds the surface unit cell parameter of the graphene, this delta Rx that we show here, then a failure of the interface has occurred. So we performed many molecular dynamics simulations under different forces imposed on the system and under different temperatures, and measured the time to failure as a function of these stresses and temperatures. And the results look something like that here. We have results for the pristine graphene, the defective graphene, and the graphene oxide. This is the time to failure of the interface as a function of the imposed force or shear stress, sigma zx, for a variety of temperatures. The higher the temperature, the shorter, of course, the time to failure. Now, one observes several things in the output of these simulations. When the stress is higher than a certain limiting value, which we call sigma limit here, one sees that the results for all the temperatures collapse onto a line into this log-log plot, which has a slope of -1/2. What happens here is that the interface fails in a barrierless fashion, and the graphene starts accelerating with respect to the polymer, hence this -1/2 power in the dependence. If, however, the stress is lower than this limiting stress, you have a very interesting behavior which suggests a thermally activated process. The time to failure essentially follows what one could call an extended Boltzmann-Arrhenius-Zhurkov expression, where you see that there is essentially an exponential here, which has kT in the denominator, and in the numerator, it has an activation energy, U0, and also an activation volume, gamma, that couples to the imposed stress. The plots of this extended BAZ model are these broken lines, and they describe the results quite satisfactorily. Now, one can compare the different types of interfaces in terms of these parameters, the U0 and the gamma. And one sees that the interface between the epoxy and the graphene, the pristine graphene, is quite weak. Its U0 is quite low. If one has defects, and even more, if one has these OH groups, the graphene oxide, this U0 rises, the interface is strengthened, and it is more difficult to destroy it. Also, one sees that the activation volume, this gamma, which is a measure of how delocalized essentially this process of failure of the interface is, it depends quite a bit on the type of the interface. It is quite large for the pristine graphene and even larger for the defective graphene, suggesting a delocalized failure process. However, for the graphene oxide, it is quite small. And this, we think, is related to the fact that the failure really initiates at an individual OH polymer association. These OH groups associate with polar groups in the polymer. And if such an association breaks, this is the onset for a failure of the interface, which is more localized than in the case of the other types of interface. Here is what happens pictorially when you have a graphene oxide inside the epoxy, and you impose a stress which is lower than the limiting stress. So when you impose the stress, initially nothing happens, but then the system fails, and it is stick-slip behavior ensues, where you see that the graphene slips with respect to the polymer, and the velocity of the stick-slip behavior one can actually estimate quite well from the failure times and the surface unit cell of the graphene. So to conclude, in polymers, we have a tremendous challenge associated with long times and long length scales. And this challenge can be met through careful design of statistical mechanics-based multi-scale modeling methods. We saw that connectivity altering Monte Carlo helps quite a bit in equilibrating polymer melts of very large molecular weight. If one cuts and pastes chains, or always observing the rules of the Monte Carlo, one can equilibrate the long length scale conformational properties of chains in a melt many orders of magnitude faster than, say, with molecular dynamics. And one can then take these well-equilibrated configurations and subject them to topological analysis to learn about entanglements. If one wishes to look at the rheology, to look at the dynamics of polymers, one must necessarily go to mesoscopic or coarse-grained methods, and one should say quite aggressively coarse-grained methods. I described such a method, which is a hybrid particle field Brownian dynamics kinetic Monte Carlo, in which the parameters and the effective force field are derived bottom-up from atomistic simulations of low molecular weight analogs, and this can capture linear and non-linear viscoelastic properties. You can capture zero shear viscosity, it can capture shear thinning, first and second normal stress differences, G prime and G double prime, and it can also show you what happens in the chains, what is responsible in terms of the long-range conformational properties and orientation of these chains for this complex nonlinear viscoelastic behavior of polymers. The glasses are a great challenge for simulation. We use this idea that a glass is configurationally arrested in the vicinity of a minimum within a basin. So a quenched average over minima can give us volumetric and elastic constants. If we want to look at the relaxation of a glass, how its properties change with time, this landscape picture of the system going from minimum to minimum across a saddle point in multidimensional configuration space seems to be useful. We can calculate rate constants, and then we can incorporate this picture into a picture of a network of minima that is progressively augmented as time goes by, and see how the probability of occupancy of these minima evolves with time. And remarkably, the way in which this probability of occupancy evolves seems to indicate specific segmental relaxation events, which are also observed experimentally in a glass. And we have also seen some ideas for how to simulate failure of a nanocomposite interface between, for example, a graphene or a modified graphene and an epoxy resin. In general, one could say that achieving a seamless connection between electronic, atomistic, mesoscopic, and continuum approaches, which nowadays can also be aided by machine learning, is quite fruitful, and it is leading to practical computer-aided materials design tools that can be applied in an industrial setting. And of course, the source of all this is statistical mechanics. If we know it well, and if we have reasonably good force fields, or can develop reasonably good force fields based on quantum mechanical methods, then we can use our imagination to carry out these simulations to long times. I would like to thank my collaborators who did the work that I described, and all those who supported it financially. And mostly, I would like to thank you for your attention and patience.
Professor Doros Theodoros, thank you so much for the presentation. We are now open to questions. If you want to participate, please enable your microphone or write it down at the chat and we will read it. Also, our YouTube viewers can write it down too. So who is going to be the first one to ask a question?
Fred.
Go ahead, Professor.
Doros, thank you very much for your presentation, for the seminar. It was wonderful. And before I start, I want to congratulate you about the 4 medals that we forgot to mention. And beside the Prounce Award,
thank you very much. Thank you.
Guggenheim medal, I think this one is very nice recognition for your work for the literature.
I'm very grateful.
Yeah. let I there's a lot of questions, but let I select some here. About the first part of your presentation, you talked about a very coarse-grained model for entanglement. And
Yes.
I wonder, can we estimate well this parameter for this model to describe more specific polymer, or it's more for qualitative behavior rather than for quantitative specific polymer?
This is a very good question. Now, the intention here, Fred, is that we derive the parameters needed for this entanglement representation from the atomistic simulations. Essentially, what we need is, first of all, the density of entanglements, and this can be obtained by this topological reduction that I showed you, if you remember this movie. So this density of entanglements, which is, of course, dependent on the chemical constitution of the polymer, you can obtain from this topological analysis at the atomistic level. And also you need a friction factor, which really describes this slippage of these slip springs along the chains. And that, again, we try to calculate from atomistic molecular dynamics. For example, you can take a non-entangled polymer, and you can observe how the diffusivity changes with molecular weight. And it is well known that for a non-entangled polymer, the diffusivity is essentially kT over n times zeta, where zeta is the friction factor and n is the length. So you can extract the friction factor. So you get these parameters, and then you incorporate them in the mesoscopic simulation. This is the intention. So as to parameterize the mesoscopic simulation on the basis of the atomistic simulations. Because, I mean, unfortunately, these slip springs have to be introduced there, because on one hand, we cannot do atomistic molecular dynamics for very long chain polymers.
Oh,
we cannot reach the required times. And on the other hand, the mesoscopic model is so soft that the chains can't entangle. In other words, because you coarse grain so much, the potential of mean force is so soft that the chains go through each other. So that's why these slip springs have been introduced. Many people have used them, and they seem to do a good job. I mean, the idea goes back to Sam Edwards, who used slip links, as he called them, to describe elasticity of polymer networks. But then people used slip springs, people like Masubuchi and Markus Müller, and then they found out that slip springs would be more realistic, so that is what we're using.
Very interesting. Can you calculate all the kind of properties like I don't know, mixing of polymer or with this model, coarse grain model?
Yeah, yeah. With the coarse grain, with atomistic, of course we can. In fact, now we are in an effort to get chi factors, as they call them in polymer science, from atomistic simulations, essentially to get the Gibbs energy of mixing as a function of composition for atomistic models. And there, I should say that Kirkwood-Buff theory has been quite useful to us because it does not require insertion of molecules. Clearly, you can do that if you calculate the chemical potentials, but you cannot insert a very big molecule inside a condensed phase, whereas Kirkwood-Buff, if you account for the system size effects, etc., is a very good tool. Now, at the mesoscopic level, which is a very important question, really the way we do it here is we rely on an equation of state model. In other words, for this polyethylene, we use the Sanchez-Lacombe, which is quite good if you fit it. It has 3 parameters. It has 3 parameters.
Simple, but okay.
It's very simple, yes.
Yeah.
And then if you have a blend, then you would also have a free energy for the blend as a function of the composition. And that is the way you would go for a blend. We are now trying to really extend this to multi-component polymer systems. So this is the way we go about it. And also, we're also interested in systems which may have nanoparticles inside them. So nanocomposites, in other words, and how these would modify the rheological behavior. And there too, we essentially have interactions of a hammaker type between the the nanoparticles or the colloidal particles. So that is the way we represent the free energy at a coarse-grained level.
Okay, very interesting. Let me ask you about the TG.
Yes.
You use WLF, the William Landau, and
we use the WLF. Yes,
yeah.
we essentially, we essentially try to get TG out of the segmental dynamics. I think it is here. Yes.
Yeah.
So
exactly.
essentially, if you do a melt, you can probe the segmental dynamics. Of course, even that is not possible for very long times, because when you run out of computer time. So even this, you have to rely on a certain form of the correlation function. And typically, these correlation functions, P1 of t, are of a so-called modified KWW form. They are stretched exponentials. So essentially, you can fit a stretched exponential to whatever part of this function you can get out of the molecular dynamics simulations. These are the more bold parts that are shown here. And then the rest is really extrapolation based on the KWW expression. And then you can integrate this P1 of t and calculate tau c. That's the correlation time for segmental motion. Now, we plot this as a function of inverse temperature, and there are several things one can do here. What we typically do is we fit that to a WLF or a Vogel-Fulcher-Taman, which is exactly the same thing. It's mathematically equivalent. And from that expression, we calculate as a parameter this TG. Of course, one can try to get TG in other ways. For example, one can cool a melt and try to see where this break in specific volume versus temperature or specific enthalpy versus temperature arises.
That's my question. That's my question, exactly.
Now, this is, of course, a very valid way of doing it. However, it tends to give you shifts in the TG because the cooling is extremely fast. When you cool with molecular dynamics, you typically cool very fast, which means that you have a too high TG. Whereas this type of observing the relaxational process is not dependent on a cooling rate. That is its only advantage. So if one cools very, very slowly and sort of corrects for the rate of cooling, one can use the break in the volume versus temperature, enthalpy versus temperature curve, and it is not so different from the one that you get from the dynamics. But in many cases, for very fast cooling, you tend to lock the system in a glassy state too high, at too high temperatures because of the very fast cooling.
Yeah, that's one of my questions. It's nice that you compare that. I didn't know about this method. So I normally thought about the density against temperature.
Yes,
but I think I agree with you. But when you do a quench, how will you guarantee looking at the free energy length scale that you have shown us a lot of minima? How you get
that is exactly the problem.
Point?
That is exactly the problem, Fred, that if you do a quench, you don't really give the system sufficient time to wander into different minima. So the relaxation is much more incomplete than it would at a slower rate. If you cool at a slower rate, then of course the system has more time to diffuse out into these other minima. Therefore, it relaxes better. And that is really the problem with glasses. And that is why we are trying to develop this landscape-based picture, because in theory, it would be able to track arbitrarily slow processes. When you do transition state theory, if you estimate the barrier correctly, it doesn't matter how high this barrier is, you see? And that's why we're really trying to develop this transition state theory approach, because it would give us access to very high barriers, which means it would enable us to look at the long time dynamics without doing molecular dynamics, because molecular dynamics necessarily will be trapped by the high barriers and give us something that is poorly relaxed. If one is interested in something which is very rapidly quenched, molecular dynamics is clearly a representative method. But if one is interested in rates on the order of 1 degree centigrade per minute, for example, which people typically use in calculating TG, molecular dynamics cannot really inform you about that, unless you do very bold extrapolations with respect to the cooling rate.
Thank you, Doros. Let people ask.
Let's see if we have any more questions. No one has raised the hand in the chat. So I think our time is almost over. I want to thank everyone for this discussion. And once again, thank you, Professor Doros, for the presentation.
Thank you very much for the invitation and the chance to interact with you. All best wishes.
Thank you.
Thank you. Goodbye.
Bye. So our seminars are being recorded and posted on YouTube, of course. After the invited lecturers agreement, please check them out on our YouTube channel. I think someone from the committee are like about to share the screen for the final announcement.
Professor Doros?
Stop sharing my
Yes,
screen.
thank you.
Okay.
Thank you, Professor. Sorry.
I think it's okay now.
Yes.
So let me say again, our seminars are being recorded and posted on YouTube, of course. After the invited lecturers agreement, please check them out on our YouTube channel. This is our organization committee. We are responsible for inviting and communicating with the lecturers. We also handle social media, video editing, certificate rights, and hosting. Thank you all for being here today. We'll meet again next Thursday on the same date that will be given by Professor Walter Chapman, entitled For Huygens Revisit Solution Non-Idealities Due to Molecular Size, Polarity Induction, and Hydrogen Bond. Let's see if Professor Chapman is in the audience so he can give
he's not.
Oh,
He's
okay.
not.
So see you all next Thursday. Thank you.